video, we're going to look at taking carboxylic acids and converting them into esters under acid-catalyzed conditions. And this is a reaction that is also known as the Fischer Esterification. So if you want to take a look at the general reaction, we would be starting with a carboxylic acid. And we're going to be converting it into an ester. And if we look at the structure of the carboxylic acid and the structure of the ester, we should notice that what we have been calling the leaving group on that carbonyl carbon is not that different between a carboxylic acid and an ester. The difference is we replaced a hydrogen with a carbon group. In terms of basicity, though, a hydroxide ion and an alkoxide ion are roughly about the same. So in order to have this reaction occur, we need to kind of play with the equilibrium and push it in the direction of the ester. And so it is going to be an equilibrium because these two leaving groups are about of the same ability. But the way that we can drive this forward is by using an excess of the alcohol. So typically we will use that alcohol as a solvent. We need an acid catalyst as well. And so having an excess of that alcohol will help to push the equilibrium towards products. The other byproduct of the reaction, when this OH leaves under acid catalyzed conditions, it leaves as water. So this is a byproduct. And so another way that you could push this equilibrium forward is maybe to remove the water as it's formed. So this can be removed as it's formed. So let's take a look at an example. So let's say that we are starting with this 4-carbon atom, carboxylic acid, so 1, 2, 3, 4. So this is butanoic acid. And let's say we wanted to make this into the ethyl ester. So we'd want to be making this into ethyl butanoate. So in order to do this reaction, we want to recognize what we're adding, and we're adding this OCH2CH3, so that's going to be coming from the alcohol. So that tells us that the alcohol that we want to use here is ethanol. And then we also need an acid catalyst. So let's say we have some sulfuric acid in here. And so we recognize that we're going to use an excess of this alcohol, so we're using it as the solvent as well as the reagent. And that should help to push the equilibrium towards the product. And we want to recognize, we're going to draw a mechanism here in a moment, we want to recognize what we actually have in solution when we take sulfuric acid, a strong acid, and we dissolve it in ethanol. So strong acids, by definition, dissociate completely. So if we were to put sulfuric acid in water, we wouldn't really have any sulfuric acid molecules in there. We would have H3O+. And so the same sort of thing happens with an alcohol. What you actually have in solution would be the protonated ethanol. So that would be the actual acid that you have present in solution. And just a small amount of that, because you're only using a catalytic amount of acid. So you would have that alcohol, the protonated alcohol. So this is available to act as an acid if you need to have a proton transfer. And then most of your solution is going to be the neutral alcohol. And so this can act as the nucleophile in the reaction. And it could also act as a base in the reaction. So we're going to go through and draw the mechanism now. So whenever you have a carbonyl under an acid-catalyzed process, the first step of the reaction mechanism is always going to be protonation of that carbonyl oxygen. So you'd want to recognize, so I'm just going to start from this butanoic acid and make the mechanism go down the page. So we want to recognize that we have that protonated ethanol. This is the acid that's available in solution, and that the very first step is going to be that the carbonyl carbon will be protonated. And so what that does is it makes the carbonyl carbon more electrophilic. So all of these steps are equilibrium steps. I'm just going to draw equilibrium arrows between them. So there we have the protonated carboxylic acid. So now this is more electrophilic so that it can react with even a weak nucleophile such as a neutral alcohol. So the next thing that's going to happen is that neutral alcohol is going to attack the carbonyl carbon. And so when it does, we're now going to have 4 single bonds to this carbon. So that is going to be a tetrahedral intermediate. So we will draw that down here. So we have an OH, another OH, and we have added the ethanol. So we only formed a bond between the oxygen and the carbon. We haven't broken any bonds, so we should still have the ethyl group and the hydrogen attached to this oxygen, which means that that will have a positive charge. And so we need to do some proton transfers here. We want to lose one of these OH groups as water, which is one of the byproducts in the reaction. So that means that we want to make one of these into a good leaving group by protonating it. But before we do that, we're going to need to deprotonate this oxygen. We only have a catalytic amount of acid, so it's not so strongly acidic that you would see 2 protons attached to this, 2 extra protons, get 2 positive charge on this molecule. So we need to remove that hydrogen first. So we're deprotonating here. So it's all of these proton transfer steps that make your acid catalyzed mechanisms so much longer. But to keep track of them, just try to follow some of the things that I'm saying, the guiding principles, right? That we want to have a protonated carbonyl, that hydrogen hasn't fallen off, and then the fact that we don't want to have more than 1 positive charge at a time can help you remember when you're taking off protons. So we're taking this off and we'll get to a neutral tetrahedral intermediate, right? Because this is now neutral. And then we want to put a proton onto one of these 2 OH groups so that we have a good leaving group. So again, our acid that we have available is the protonated ethanol. So it is catalytic, right? So we used it in the first step. We regenerated here. We're going to use it again, and we're going to regenerate it again later. So this alcohol can be protonated by reacting with this acid. And so it's going to make a good leaving group. So we can draw this with a good leaving group now. So we have the OH, and I got a little excited and put the pi bond in a little bit too early. That's going to come in the next step, so let's get rid of that. So we've got this OH, this one has been protonated, so it is now a good leaving group. And we have the OCH2CH3. Right, so now that we've got this set up with a good leaving group, we can have it leave. So now I can form that pi bond that I was so eager to make and break off the bond to the leaving group. So now it's going to be really, really close to that ethyl butanoate. So these mechanisms are long, so hopefully you can follow how we're going around here. We have one more intermediate, and then we'll be actually at that product. So now we've formed a pi bond. So that oxygen is protonated, and we have the OCH2CH3, right? So we said we used acid in the first step, we regenerated it here, we used it again here, and now we're going to regenerate it again in this very last step because I'm going to use an ethanol to take off that proton. And so this is going to be the final step in this mechanism. All right, so a little bit long, but there you have it, the full mechanism for the Fischer esterification.